Section 12.3, Elasticity. This is our last section, and it's expanding a bit upon our previous sections looking at equilibrium. Because anytime we have these problems in the xy plane, we have three independent equations, right? F net in the x direction equals 0, F net in the y direction equals 0, torque net is equal to 0. Having three equations, we can solve for three unknowns. But if we ever have more unknown forces, more than three forces we don't know, we can't solve for them. The situation is known as indeterminate. Now, these indeterminate situations assume that bodies are rigid and don't deform. It turns out there are no such bodies. Everything deforms slightly. So with some knowledge of elasticity, we could potentially solve more problems. This is also very relevant to materials engineering or materials science. So if you take a class of materials, this is a lot of what you will be seeing. So continuing on, all rigid bodies are partially elastic, meaning we can change their dimensions by applying forces in different directions. So a stress or deforming force per unit area, that's a key detail there. Stress is equal to force divided by area. That's an equation. Produces a strain or a unit deformation, which we'll see is often just a change in a dimension divided by the original dimension. We'll see both of those in specific examples in a moment. Now, there are three main types of stress, three different ways to apply a force that will change or deform an object. One is our tensile stress. That says if you have an object that has some length, you can stretch it out, apply that tensile stress, and its new length will be the original length plus some length there. So taking an object and stretching it, it can then become longer under that force being applied. Now, another type that we could have would be shearing. And this one, instead of stretching it, it's sort of like knocking it over, it's pushing it to one side. This is a little easier to see with something like a textbook, where with the textbook, I'm not going to try and stretch the textbook wider, but I could push it over, and we see that it's now, the top edge is not pushed over relative to the bottom edge because I've applied a force perpendicular to that length there. Finally, the last one is hydraulic, and this one you can imagine being in a liquid or a gas and having pressure coming in from all sides, and that changes the volume of something. Like if you put a balloon in gas, and if you change the pressure, that will exert a force on all the sides of the balloon, and the balloon might then compress. There'd be some change in volume. Now, these quantities of stress and strain, it turns out, are proportional when we're in what's known as the elastic range. They're related by something known as the modulus of elasticity, which there are some different ones for our different types of stress. But our basic form of our equations are going to be that stress is equal to some modulus, which is just a constant given a material, times the strain. So as stress increases, as you apply more and more force, eventually a yield strength is reached and the material deforms permanently. So that's, if we look at this plot, this is a plot of stress versus strain, right? Noting that stress is equal to the modulus times strain. So here we have strain. Stress would be if we're continuing to apply more and more force, like with a tensile example, stretching something out. Strain would be how it responds, how the length increases with more force. And at small values, notice this linear region, that's the elastic region. So that's the normal one. Then the yield strength is where the material will deform permanently. So you notice after you reach that yield strength, it becomes a nonlinear relationship, right? There's a space here where it's strange, right? And this is where it will be permanently deformed. So what I like to think about is an old rubber band or an old hairband where you can stretch it and it'll be elastic for quite some region. But if you keep stretching it too far, eventually it just becomes stretched out and it's a really sad hair scrunchie. No one wants that anymore, right? But it's not broken. It still is whole, it's just not very elastic, so it's not very useful. But you could keep stretching that old rubber band or old hair tie, and at some point you would be able to ultimately break it. That's the rupture, and that's known as the ultimate strength. That's where it does give way. So in simple tension or compression, our tensile case, the stress is just calculated with the force divided by the area, where the area is going to come from these end caps in the picture here. So you could imagine this circle, we want to find that area. And then the force being applied to said area. The strain is that dimensionless quantity of delta L all over the original length, so how much longer it is divided by how much it started at. And then what we use for the tension and compression modulus is known as Young's modulus, and it's the symbol in our book is a capital E, so that's fine, that works. And something to note is that many materials have very different tensile and compressive strengths despite the same modulus being used for both. So concrete, for example, has a really high compressive strength but a low tensile strength. And that's one reason why we use concrete in pavement on the ground, because it's really good at taking the compression of having cars drive all over it or trucks. But we don't use concrete so much in bridges where there might be some tensile stretching of it. It wouldn't be very secure and the bridge would be pretty sad. So the Young's modulus E is something you're not expected to know, but that's something you can look up in the table. So here's a table of Young's modulus for several common materials, so you can get a sense of the comparison, right? So steel has a pretty large Young's modulus. And then we could go down, concrete is smaller, bone, polystyrene, very small. So the larger the Young's modulus, that's going to be the larger effect that we could see, right? So if we go back to thinking about that equation that we saw, that the force divided by the area is equal to Young's modulus times delta L over L. There we go. So what we get here is, hey, if we increase, if we have a larger Young's modulus with a larger force, what would that do to the delta L? Well, if we solve this for delta L, then what we would find is that delta L is going to be proportional to the force, but it's going to be proportional to force divided by Young's modulus. So if we have a larger Young's modulus, we don't see the same amount of stretching or compressing. So steel exhibits the least amount compared to wood or bone or polystyrene, right? You can imagine styrofoam basically. It's going to stretch more than steel. That matches our expectations. And for an extreme example of this, whoops, too far, you could look at Kevlar, which has a tensile strength of 3,620 megapascals, which notice are the units of these Young modulus, that they are all 10 to the 9 newtons per meter squared, which newtons per meter squared are pascals, and the mega is 10 to the 9, or 10 to the 6. I forget my larger SI units. Let's double check. Mega is 10 to the 6, excuse me. So, so this one Kevlar, it has a huge tensile strength, which is known as the same as the ultimate strength. And that's why it's used in bulletproof vests, because it's it's a lightweight material. It's not very comfortable to run around in steel plating, but Kevlar is lightweight. You don't need a thick amount of it, and it's strong. It won't break very easily. So that's a great comparison to keep in mind. Right, now strain could be measured, for instance, by a strain gauge. So there's one shown here. You place it on the material, and so it becomes subject to the same strain. If the whole thing is stretching apart, it will stretch apart too. You notice there's like these bars that are interlaced, and so as they stretch, it can be read as actually a change in electrical resistance for strains up to 3%. 3%. Notice this isn't a huge change in length relative to the original length, but it's something that can be measured, and something that becomes really important when you are designing structures and considering which materials to use for various applications. Right, now our other forms of stress are, we have shear, and for shear, we're going to use the shear modulus, which is a capital G. So that's another constant that's usually just given to you in a problem. The shear is still applied as force divided by area, where it still is that cross-sectional area of the top. But this time, instead of being delta L over L, it's delta X. It's how much we've knocked it off to one side. Relative, though, to the same original length or height, if you want to view it that way. So notice delta X is actually along a different axis than L. The shear is telling you about how you can sort of warp it, pushing it sideways, perpendicularly. And then for the hydraulic compression, we use the bulk modulus B. We'll also, instead of using force over area, use something known as pressure, which we're going to be seeing more of in chapter 14. So there's more coming with that, but you can know for your own reference now, for now, that pressure is actually equal to force over area, but they could give it to you as a pressure and then relate it to the change in volume relative to the original volume there. So these are other examples of seeing stress and strain in practice. And here's a demonstration of a shear transformation, right? We have the nice square, and then it gets sheared off to one side. Further example, we have a sheep, and then we have a sheared sheep. So hopefully you all are amazed at that. Yep. All right, one example to wrap up. Stress and strain of an elongated rod. One end of a steel rod of radius R is 9.5 millimeters and length L is 81 centimeters is held in a vise. A force of magnitude 62 kilonewtons is then applied perpendicularly to the end face, uniform across the area, at the other end, pulling directly away from the vise. What are the stress on the rod, the elongation delta L, and the strain on the rod? The key here is figuring out, if we want to solve for stress, elongation, and strain, what are those equations, right? So we remember, okay, stress, that's our force over our area. Delta L is related to the stress, right? We solved for it as the stress divided by Young's modulus times the original length, and strain is related to the elongation. It's just elongation divided by the original length. So once we figure those things out, the rest of this problem follows more naturally. And we'll go ahead and look right now at this solution, right? So stress is force over area. Here it matters that tells you that it's a steel rod. And so the fact that they give you the radius tells you how you can calculate that area of the end cap. So that you calculate it with the area of a circle, pi r squared. And the force is as given, converting the units properly, right? So 62 kilonewtons becomes 6.2 times 10 to the 4. 9.5 millimeters becomes 9.5 times 10 to the minus 3 meters. And so then you get your stress, which does have units of force over area, newtons per meter squared. For the delta L, we start with that original equation, and as mentioned, divide the stress by Young's modulus and multiply by the length. And the key here, we have the stress from part A. We also have the length given, which we can convert to centimeters by dividing by 100 to become 0.81. The Young's modulus, we need to go back to that table and look it up. So in some of the problems, they might mention, oh, it's a steel rod. Okay, because it's steel, they're telling me something about the material. That tells me the Young's modulus. You can go to the table. You don't have to put the table on your crib sheet. The table or that information would be given to you on the exam if you need it. But it's knowing that you can look it up. Because when you do look it up, you find, oh, it's 2 times 10 to the 11 newtons per meter squared. And so then we notice when we divide this out that the newtons per meter squared cancel and we just get meters out. And so the change in length is less than a millimeter. It's pretty tiny, even though this is a huge amount of force, like 62,000 newtons is not a small amount of force. And then finally we can calculate the strain by taking our elongation, our delta L, dividing it by the original length, and that's 1.1 times 10 to the minus third, a really small amount. If you make it a percentage, it's not even 1%, it's about 1/10 of a percent, 0.11%. So here's an example of seeing all of these in practice. This section is not as important as sections 12.1 and 12.2, which are the bulk of our chapter, and there is indeed one more example for your reference if you're interested in the slides, looking at static equilibrium with the Leaning Tower of Pisa. So you're welcome to check that out on your own time. Please do feel free to ask questions. I would love to chat more.